Let's dive right into one of the biggest questions we've ever asked, something straight out of science and science fiction. It's a dream that has captivated us for generations. Is time travel actually possible? I mean, just think about it for a second. The dream of walking with dinosaurs or seeing history unfold right before your eyes, maybe even just getting a tiny glimpse of the world to come. This idea, it's so woven into our culture that it almost feels like it has to be possible, right? But what happens when we step away from the fiction and look at the hard reality of physics? What does it have to say? Can you really just hop between different eras? Or are there some fundamental rules of the universe that just can't be broken? Well, to find that answer, we have to start by completely rethinking time itself.
So first up, we have to throw out our old ideas and rethink our most basic understandings of what time even is.
You know, for most of history, we thought of time as this great universal river, flowing at the exact same speed for everyone, everywhere. One single giant cosmic clock ticking away. But then, Albert Einstein came along and just shattered that entire idea. He proved that time isn't universal at all. It's personal. It's relative. It literally stretches and shrinks depending on how fast you're moving and how much gravity you're feeling. So in a very real sense, your time and my time are not the same.
And that one idea, that single brilliant insight that time is relative, that's the key. That's what unlocks the door to even having a conversation about time travel. It changes absolutely everything.
All right, section 2. Forward travel is real. And honestly, this might be the most shocking part of this whole story.
Okay, I want you to let this one sink in for a moment. Time travel to the future is not science fiction. It is a measured, confirmed scientific fact. The laws of physics as we know them don't just allow for it, they actually guarantee it.
So how on earth does that work? Well, the principle is called time dilation. What Einstein predicted was that for anything moving really, really fast, or for anything in a super strong gravitational field, time itself literally slows down for it. The clock on a spaceship rocketing through space will actually tick slower than a clock sitting right here on Earth. And look, this isn't just some theory on a blackboard. We've measured it. The GPS satellites that your phone relies on, they have to constantly correct for time dilation, otherwise they wouldn't work at all. We've proven it with incredibly precise atomic clocks. In fact, every single astronaut who has ever been in orbit is technically a real-life time traveler. Now, of course, for our astronauts, the effect is super tiny. We're talking fractions of a second. But it is real. When they come back to Earth, they have aged just a little bit less than the rest of us. They have, in a very literal way, traveled into our future.
And here's the crucial part. This effect gets really dramatic the closer you get to the speed of light. Imagine this. You take a one-year trip on a spaceship traveling at 99.999% the speed of light. For you, on board, only 1 year goes by. But when you get back, you'd find that decades, maybe even more, have passed on Earth. You've done it. You have successfully traveled to the future.
So, okay, jumping to the future is on the table. But what about going the other way? What about going back? That brings us to section 3, the paradox of the past.
Now, believe it or not, Einstein's equations actually do allow for some pretty bizarre possibilities. The most famous one you've probably heard of, wormholes. These are theoretical tunnels through the fabric of space-time. And if you could actually create one, it might connect not just two different places, but two different times. So on paper at least, these could be our highways to the past.
So if the math kind of allows it, what's the big deal? Well, the problem is something called causality. You know, that fundamental rule of the universe that says cause has to come before effect. And traveling into the past, that threatens to just shatter that law completely. And this leads us to the most famous problem of all, the grandfather paradox. Let's walk through it. Imagine you build a time machine, you go back to the past, and you prevent your grandparents from ever meeting each other. What's the result? You're never born. But wait a second. If you were never born, then who went back in time to stop them in the first place? It's a perfect, unbreakable, logical knot.
And that's not the only one. There's also the bootstrap paradox. Picture this. A time traveler goes back and gives Shakespeare a book containing all his future plays. Shakespeare just copies them out and becomes famous. Then, centuries later, that's the very same book the time traveler takes back to him. So, who actually wrote Hamlet? The information has no origin. It just exists. These paradoxes are really deep, fundamental problems for physics.
So,
Does the universe have some kind of built-in safety net to stop these paradoxes from happening? Well, that brings us to our final section, cosmic rules and final limits.
Physicists have some really clever ideas about how the universe might solve this mess. One is called the self-consistency principle, which basically says you just can't change the past because anything you do is always part of it. Another is the many worlds theory, which suggests changing the past just creates a whole new, separate universe. And a third idea from the legendary Stephen Hawking is that the laws of physics themselves might have a chronology protection rule that just flat out makes building a time machine impossible.
So let's focus on the two biggest ideas here. With self-consistency, the past is basically set in stone. If you go back in time to stop something from happening, you'll find out that your attempt to stop it is actually what caused it to happen all along. You can't change history because you're already a part of it. But in the many worlds view, you can change things. It's just not your timeline you're changing. The second you alter the past, you branch off into a brand new parallel universe, and your original timeline is left completely untouched. Problem solved. Kinda.
But okay, let's just pretend for a second we could somehow solve all the paradoxes. There is still one more colossal hurdle, a practical one. The amount of sheer energy you would need to build one of these theoretical time machines is, well, it's simply unimaginable.
See, to keep something like a wormhole propped open long enough to actually travel through it, you would need this bizarre, exotic stuff called negative energy. And here's the thing, we've never actually seen it. It exists in our equations, sure, but for all we know, it might not even exist in reality.
So after all that, here's the final verdict from our explainer. Can we travel to the future? Yes, absolutely. It's a proven fact of physics. Can we travel to the past? Well, maybe. The math doesn't completely forbid it, but it seems to be blocked by all those paradoxes, fundamental laws of physics, and those just mind-boggling energy requirements.
You know, in the end, maybe the deepest truth is this. We are all time travelers. Every single one of us. We're all moving forward at that steady, familiar pace of 1 second per second. And while the past might be a closed book, the future is still an open road. And who knows where it's going to take us next?